Welcome to the deep dive, meticulously crafted just for you. We're not wading into the shallow end of machine learning today.
No, definitely not.
We are slicing straight to the core of modern deep learning.
That's the plan.
Today, our mission really is to demystify PyTorch, the leading deep learning framework,
It really is dominant, especially in research.
and provide you with the essential actionable knowledge you need to start building real models. We're moving past the hello world stage here.
Right. Since you have that, say, 3 to 6 months of Python under your belt, we're skipping the absolute basics.
Yeah, no print hello world today.
We're jumping straight into the architecture that, drives AI innovation.
So our goal today is precision engineering, you could say.
I like that. We need to go from the broad, almost philosophical concept of artificial intelligence.
The big picture stuff.
Exactly. All the way down to the specific mechanics, the actual lines of code that truly define what it means to train a neural network using PyTorch. We'll focus relentlessly on the primitives tensors, we'll get to those, the universal 6-step workflow, and critically, the common pitfalls.
The pitfalls. Always good to know those up front.
Absolutely. The things that inevitably plague beginners, we want to ensure you know exactly how to dodge them before they slow you down.
Makes sense. So we've synthesized tutorials, dense documentation, foundational course materials, all of it,
Yep, pulled it all together.
to create this structured blueprint for your deep learning journey. And this isn't just about reviewing syntax, is it?
Not at all. It's about grasping the core mindset you need for success. Think one part critical scientist
Meticulous, careful.
and one part relentless experimenter. You got to try things out.
Okay, scientist and experimenter. I like that. Let's dive in.
All right, so to start, let's establish our bearings. Where do we sit in this vast world of intelligent systems?
Good idea. AI, ML, DL. It gets confusing.
It does. It's best viewed as a hierarchy, maybe like nesting dolls or concentric circles. Each concept is a specialization of the last.
Okay, so the biggest container. That's artificial intelligence.
AI. Exactly. That's the big bubble. The overarching concept encompassing any system, machine, or program exhibiting behavior we traditionally call intelligent.
So really broad, like even a simple chess program could technically be AI.
In a sense, yes. It ranges from simple decision trees to, incredibly complex algorithms. It's a huge umbrella term.
Got it. Then inside that bubble,
Inside AI, we find machine learning, ML. Now, this is where things get interesting. ML is the discipline where the system learns patterns directly from data.
okay, so less explicit programming.
Right. Instead of writing out every single rule for recognizing, say, a cat, you feed the machine thousands, maybe millions of pictures of cats.
And it just learns.
It develops its own internal model of what a cat looks like based on those examples. It learns the patterns itself.
Okay, that's a key difference. Learning from data. And then the final layer.
The innermost circle inside ML is deep learning, DL. This is a specific subset of machine learning.
The deep part.
Exactly. It utilizes complex, multi-layered neural networks, hence deep, to learn hierarchical representations and highly abstract features directly from raw input data.
Hierarchical representations. What does that mean in practice?
Think about image recognition. The first layers might learn simple things like edges or corners. Deeper layers combine those to recognize textures or simple shapes. Even deeper layers combine those to recognize eyes, noses, or eventually a whole face or object. It builds complexity layer by layer.
Okay. So it learns levels of abstraction. Makes sense.
Now, the choice between using traditional ML and deep learning often boils down to your data. What does it look like?
Right. Is it neat and tidy or is it messy?
Pretty much. Traditional ML algorithms support vector machines, gradient-boosted machines, random forests. They're typically best suited for structured data.
Like spreadsheets, tables of numbers.
Exactly. If your data arrives in neat tables, rows and columns of quantifiable information, financial records, standard health metrics, census data, traditional ML often gives you excellent, predictable results.
Okay. But what about the messy stuff?
Well, the moment you move into the domain of unstructured data images, streaming video, raw audio files, natural language text like emails or articles, the game changes completely.
That's where DL comes in.
That's the domain where deep learning, specifically these complex neural network architectures, becomes pretty much indispensable. DL excels at automatically extracting meaningful features from this messy, raw data.
Which traditional ML struggles with.
Yeah, traditional methods often require a lot of manual feature engineering first. You have to tell the algorithm what to look for. DL aims to learn those features on its own.
So why do we even need ML or DL? Why not just write programs the old way?
Because sometimes the old way just fails. Imagine trying to write the explicit rules for driving a car.
Oh, wow. Yeah, that would be impossible.
Right. If the light is red, stop. If green, go. But what about a yellow light? What if a pedestrian steps out? What if it's raining, snowing? What if a car cuts you off? The list of rules would be infinite, incredibly complex, and brittle.
You'd never finish writing it.
Exactly. Instead, we use ML, often DL for something like self-driving, to learn the patterns of good driving from vast amounts of data that need to solve problems where the rules are too long, too complex, or even unknown. That's the driving force behind all machine learning.
Okay, that makes the motivation really clear. And DL applied to unstructured data, that's behind a lot of tech we use daily.
Absolutely foundational. Think about the recommendation systems on platforms like YouTube or Netflix or Amazon.
Yeah, they're creepily good sometimes.
That excellent accuracy, the way they seem to know what you want next, that's powered by incredibly sophisticated deep learning models, analyzing your behavior and comparing it to millions of others.
Okay, what else?
Language?
No.
Oh man, the advancements in language translation and speech recognition over the last, say, 10 years, it's been revolutionary.
Like Google Translate getting way better.
Exactly. The fluidity of translation, the accuracy of voice assistants like Siri or Alexa, understanding complex commands, even things like chatbots or large language models generating coherent text.
That's all deep learning.
Primarily, yes. Architectures like recurrent neural networks, RNNs, and especially transformers, which are behind models like GPT, are built on deep learning principles to process and generate language.
Right. And you mentioned computer vision earlier. Can you give an example?
Yeah, I saw a really compelling one recently. Imagine a hit-and-run accident caught on a low-resolution security camera at night.
Tough situation. Hard to see anything clearly.
For a human, yes. But you could use a dedicated object detection model, likely built and trained using PyTorch, to scan hours of that footage automatically.
Know what it'd do?
It could classify the type of vehicle, sedan, SUV, truck. It could track its movement across different frames, and then maybe combine that with other DL-powered image enhancement techniques to try and sharpen the image, potentially even identifying something as small and blurry as a license plate.
Wow. So taking messy video and pulling out actual useful information.
That's a perfect demonstration of deep learning's power with unstructured data, turning noise into signal.
Okay, so DL is powerful, essential for modern problems. Why focus specifically on PyTorch? There are other frameworks, right? Like TensorFlow.
There are. TensorFlow is certainly a major player, especially in production environments historically. But PyTorch holds a distinct and, I think, compelling advantage, particularly for researchers and anyone working on novel problems or experimenting heavily.
You mentioned it's the research favorite, used in, what, 58% of papers with code? That's huge.
It is, across something like 65,000 papers tracked.
So what's the technical reason? Why do researchers gravitate towards it?
Okay, this is the crucial insight often missed in basic tutorials. It boils down to two main things. PyTorch uses an imperative programming style and, relatedly, a dynamic computation graph.
Imperative. Dynamic computation graph. Okay, let's break those down. What does dynamic computation graph mean?
All right, so when your data flows through a neural network, all the operations matrix multiplies, additions, activation functions, they form a kind of map or a graph showing how the computation happens.
Like a flowchart for the math.
Kind of, yeah. Now, some older frameworks, in TensorFlow 1.x, for example, use a static graph. That meant you had to define the entire network structure, the whole flowchart, up front, compile it, and then you could push data through this rigid, predefined structure.
Like drawing the complete blueprint for a building before laying a single brick?
Exactly. Perfect analogy. PyTorch, on the other hand, is dynamic. The graph, the flowchart, is built on the fly as the data flows through and each line of Python code defining the model executes.
So it builds the blueprint as it builds the wall?
Sort of. It means the execution is more immediate, more Pythonic, you could say. This imperative line-by-line style makes debugging much easier. You can use standard Python debuggers like PDB or just print statements right inside your model's forward pass.
Ah, I can see how that would be helpful.
And you can use standard Python control flow like if statements or for loops that depend on the data itself directly within your model definition. The structure can change from one run to the next based on the input.
Okay, that sounds incredibly flexible.
It is. For researchers who are constantly tweaking architectures, trying new ideas, maybe having variable length inputs or conditional computations, that flexibility and ease of debugging are absolutely priceless. It speeds up the iteration cycle dramatically.
And that research momentum translates to industry, too.
Absolutely.
Yeah.
It's not just academics. PyTorch is the go-to internal framework for machine learning at Meta AI, Facebook. And Microsoft is deeply invested in the PyTorch ecosystem as well. Giants are using it for their core ML work.
So learning PyTorch means you're learning the language that's driving a huge amount of innovation from university labs right up to the biggest tech companies.
Precisely. You're aligning yourself with where a lot of the cutting-edge development is happening.
Okay, now that we know why we're focusing on PyTorch, let's get into the nuts and bolts, the mechanics.
Right. First principles.
Before we can build any kind of model, an engine as you called it, we need the raw material it's made of. And in PyTorch, that material, that fundamental unit, is the tensor.
Everything is a tensor. Your input data images, text converted to numbers, tables, the model's internal parameters, the weights and biases it learns, the intermediate calculations, the final output. It's all tensors.
So what is a tensor, fundamentally?
Think of it as the numerical encoding of your data. It's the basic building block. If you're familiar with NumPy arrays,
Sure.
a PyTorch tensor, torch.tensor, is very similar. It's a multi-dimensional array of numbers. But critically, it's supercharged for two things: running incredibly fast on GPUs.
Graphics cards, right, for parallel processing.
Exactly, and for automatic differentiation. That's the magic that lets PyTorch calculate gradients for training, which we'll get to. It's designed from the ground up for deep learning.
Okay, now we hear these math terms, scalar, vector, matrix. How do they relate to tensors?
That's just nomenclature based on the tensor's number of dimensions, or ndim as it's called in PyTorch. They are all technically torch.tensor objects.
So a scalar?
A scalar is just a zero-dimensional tensor, a single number, like torch.tensor 7.
Just one value?
Yep. And if you actually need that raw Python number back, say for printing or some calculation outside PyTorch, you use the .item method on the scalar tensor.
Okay. And a vector?
A vector is a one-dimensional tensor. Think of it like a list or a single row column of numbers. Torch.tensor, 1, 2, 3.
Right. And a matrix?
A matrix is a two-dimensional tensor, your classic grid or table of numbers, rows and columns. Torch.tensor, 1, 2, 3, 4.
Okay, 0D, 1D, 2D. What about higher dimensions? You mentioned images earlier.
Exactly. When we deal with more complex data, we get into higher dimensional tensors. An image might start as 3D. You typically have dimensions for height, width, and color channels like red, green, blue.
So maybe like 224 pixels high, 224 pixels wide, and 3 color channels. A 3D tensor.
Precisely. But then when you feed images to train a network, you don't usually feed them one by one. You feed them in batches.
Right, for efficiency.
So if you have a batch of, say, 64 images, your tensor suddenly becomes four-dimensional. The first dimension is usually the batch size, so it might be 64, 3, 224, 224. Batch size, color channels, height, width.
Got it. The dimensions tell you the structure of the data inside the tensor.
Exactly. And shape is absolutely critical in PyTorch. We'll come back to that when we talk errors.
Okay. Now, how do these tensors relate to the actual learning process? Do networks start knowing things?
No, not at all. Neural networks start out, well, kind of dumb. They start with random tensors. The model's initial parameters, its weights and biases, are typically initialized with random numbers drawn from some distribution.
So just guesses at first.
Essentially, yes. PyTorch makes creating these random tensors really easy with functions like torch.rand, which gives you numbers between 0 and 1 from a uniform distribution, or torch.rand, which gives you numbers from a standard normal distribution, means 0 variance 1.
Okay.
The entire training process is then about taking these initial random values and gradually adjusting them based on the data and the errors the model makes until they stop being random and start accurately representing the patterns in your data.
So learning is just nudging random numbers in the right direction over and over.
That's a great way to put it. Millions of tiny nudges.
Okay. So we have tensors for individual data points or random weights. How do we handle large collections of data, like a whole data set of images?
Good question. This is where PyTorch provides some essential tools for code modularity and, frankly, sanity. You want to keep your data loading and pre-processing separate from your model training logic.
Decoupling, right, makes the code cleaner.
Exactly. It relies on two core data primitives, usually found in torch.utils.data.
Okay, what are they?
The first is torch.utils.data. Dataset, think of this as the blueprint for your data. It's a Python class you typically define yourself. It needs to implement two key methods. len, which tells PyTorch how many samples are in your dataset, and getItem, which defines how to retrieve a single sample, like an image and its label, given an index.
So the dataset knows where the raw data is, like image file paths and how to load and maybe transform one item.
Precisely. It handles the logic of opening files, maybe resizing images, converting text to numerical tokens, whatever preprocessing is needed for a single data point. Here it holds the samples and their corresponding labels.
Okay, that's the source. What's the second primitive?
The second, and incredibly useful one, is torch.utils.data, data loader. This primitive takes your dataset object as input and wraps an iterable around it.
An iterable, so you can loop through it.
Yes, you can easily loop through your data, but the data loader does much more. Its main job is to efficiently fetch the data from the dataset and, crucially, organize it into batches or mini batches.
Ah, the batches we talked about for training.
Right. Modern datasets can be huge, millions or billions of items. You can't possibly fit all that into your computer's RAM, let alone the GPU's memory, all at once.
Makes sense.
So we process the data in smaller chunks, these mini batches, maybe 32, 64, or 128 samples at a time. The data loader handles slicing the data set into these batches automatically.
Does it do anything else?
Oh yeah. It can automatically shuffle the data at the beginning of each epoch, each full pass through the data set. This is vital to prevent the model from learning biases based on the order of the data.
Good point. Keeps it random.
It can also use multiple worker processes to load the data in parallel in the background while the GPU is busy computing. This prevents the CPU data loading from becoming a bottleneck and keeps your expensive GPU fed.
So, dataset holds the map to the data. Data loader handles batching, shuffling, and parallel loading. Much cleaner.
Much cleaner and much more efficient.
Okay, so now we have our data neatly packaged into batches of tensors by the data loader. What happens next inside the network? You said it's basically math on tensors.
It is. At its heart, a neural network is just a sequence of mathematical operations performed on tensors. While PyTorch and its nn.Module abstract away a lot of the details, understanding the fundamental tensor manipulations is absolutely non-negotiable, especially for debugging.
Debugging sounds like we'll need it.
You will. You'll encounter basic operations all the time. Adding a scalar, tensor plus 10, subtraction, element-wise multiplication, tensor. These usually work as you'd expect if you're familiar with NumPy.
Okay, standard arithmetic.
But the operation you must understand intimately, the backbone of how layers connect and transform information, is matrix multiplication. In PyTorch, you'll primarily use torch.matmul, or the @ operator.
Right, multiplying grids of numbers. This sounds like where those shape errors might creep in.
Bingo. Matrix multiplication comes with strict, unforgiving rules. Get them wrong, and your code crashes. It's probably the source of, I don't know, maybe half of beginner errors.
Okay, rule number 1.
Rule 1. The inner dimensions must match. If you have two matrices, A and B, and you want to calculate A multiplied by B, A at B, the number of columns in matrix A must be equal to the number of rows in matrix B.
Inner dimensions, columns of the first, rows of the second.
Exactly. So if A has a shape of 5, 4, 5 rows, 4 columns, and B has a shape of 4 rows, 3 columns, you can multiply them because the inner dimensions 4 and 4 match.
Okay, what if B was, say, 6, 3?
Then A at B would fail instantly, runtime error, because 4 does not equal 6.
Got it. Inner dimensions must be identical. Rule number 2.
Rule 2. The outer dimensions define the resulting shape. The shape of the matrix that results from the multiplication is determined by the number of rows in the first matrix and the number of columns in the second matrix.
Outer dimensions, rows of the first, columns of the second.
Right. So in our example, A5, 4 multiplied by B4, 3, the inner dimensions 4, 4 match. The outer dimensions are 5 and 3. So the resulting matrix C equals A at B will have the shape 5, 3.
Okay, 5, 4, 4, 3 gives 5, 3. That seems logical.
It is. But it's easy to forget when you're dealing with complex models. Now, because of Rule 1, the inner dimension requirement, you'll very frequently find yourself needing to transpose a tensor.
Transpose, like flipping it.
Exactly, flipping its axis. If you have a tensor T with shape 3, 4, its transpose, often written as TT, will have the shape 4, 3. You often do this just to make the inner dimensions align correctly so the matrix multiplication can actually happen.
Ah, so transposing is a tool to satisfy Rule 1.
It's a very common tool, my advice. Constantly print out tensor.shape. Know the shapes of your tensors at every step. Understand these two rules of matrix multiplication. If you do that, you'll eliminate a massive class of frustrating errors right from the start. Okay, so we've got tensors, we know how to load data with dataset and beta loader, and we understand the critical matrix multiplication rules. Now let's connect this to the bigger picture.
The overall process.
Right. The entire deep learning process, whether you're building a simple linear model or a giant complex network like GPT, generally follows a structured universal workflow. It's like a repeatable blueprint you can use for almost every project.
Having a structure like that is super helpful. It takes something that feels kind of abstract and magical, the network learning, and breaks it down.
Exactly. It breaks it into concrete, manageable steps. There are essentially 6 core steps.
6 steps. Okay, let's walk through them. Step 1.
Step 1, get data ready. This is everything we just discussed in the last section. Turn all your raw input data into numerical representations torch.tensor format. Then, prepare and organize them using dataset and data loader for efficient batch processing. Get your fuel ready.
Data prepped and batched. Got it. Step 2.
Step 2, build or pick a model. The model is the computational engine. It's the structure that defines the sequence of mathematical operations, the tensor math, that will transform your input data into predictions.
So this is where we define the layers, like linear layers or convolutional layers.
Precisely. If you're building a custom model from scratch, the standard practice in PyTorch is to create a Python class that subclasses torch.nn.Module. This is fundamental.
Why nn.Module specifically?
Because n.Module does a lot for you behind the scenes. It's not just a container. It automatically tracks all the learnable parameters within your model, the weights and biases. It provides handy utility methods, like model.to device, for easily moving the entire model and all its parameters to a GPU or CPU.
Okay, so it manages the model state.
Yes. And crucially, when you subclass nn.Module, you must implement or overwrite a specific method called forward.
The forward method, what does that do?
The forward method defines the computation flow. It dictates exactly how input data X passes through the layers you've defined inside your model to produce an output. It's literally the forward pass calculation.
So you define the layers in the init method of the class, and then you define how data flows through them in the forward method.
That's the standard pattern, yes. Now, the actual learnable parts of the model, the weights and biases that start random and get adjusted, they need special treatment.
How so?
You typically define them inside your nn modules init using torch.nn.parameter. It looks like you're just creating a tensor, maybe a random one, but wrapping it in a parameter tells PyTorch. This is a value that I want you to track, calculate gradients for, and allow the optimizer to update during training.
Ah, okay. So nn parameter flags it as learnable.
Exactly. So think about the learning process again. The model starts with these random n-parameter weights and biases. It looks at the input data batch via the forward method, performs calculations, makes a prediction. Then we calculate how wrong it was.
Which leads us to step 3.
Leads us perfectly to step 3. Pick a loss function criterion. Once the model spits out a prediction in the forward pass, we need a way to measure how good, or more often, how bad that prediction was compared to the actual target value, the ground truth label.
We need to quantify the error.
Precisely. The loss function does exactly that. It takes the model's prediction and the true value, and it outputs a single scalar number representing the error or loss. The goal of training is to minimize this number.
What are some common loss functions?
Depends on the task. For regression problems like predicting a house price, you might use mean absolute error, MAE, which in PyTorch is torch.nn on L1 loss, or mean squared error, MSE, nn.MSE loss. For classification problems, is it a cat or a dog, you'll often use cross-entropy loss, like n.cross-entropy loss or nn.BCE with logits loss for binary classification.
Okay, so the loss function gives us a score for how wrong the model is. Step 4.
Step 4. Pick an optimizer. Knowing how wrong you are, the loss, is essential, but it doesn't tell you how to fix it. You need a strategy for updating the model's parameters to reduce that loss.
That's the optimizer's job.
Exactly. The optimizer contains the algorithm that implements the update rule, typically based on some form of gradient descent. It uses the gradients calculated during backpropagation, we'll get there, to adjust the model's learnable parameters, n-parameter tensors, in a direction that hopefully minimizes the loss.
Where do we find these algorithms?
They live in the torch.optim module. Very common choices are torch.optim.sgd, stochastic gradient descent, and torch.optim.atom, adaptive moment estimation, which is often a good default choice as it adapts the learning rate per parameter.
Okay, so loss function measures error. Optimizer figures out how to fix it based on gradients.
Right, and the optimizer uses those gradients along with a crucial hyperparameter you set, the learning rate.
Okay, before we hit step 5, let's quickly clarify. Parameters versus hyperparameters. You just mentioned the learning rate is a hyperparameter.
Good distinction to make. Model parameters are the values inside the model that are learned during the training process. These are the weights and biases, the things wrapped in n parameter. They start random or pre-trained and are adjusted by the optimizer based on the data.
Things the model learns itself.
Right. Hyperparameters, on the other hand, are the configuration settings outside the model that you, the machine learning practitioner, have to set before training begins. You control these.
Things we set to guide the learning.
Exactly. Examples include the learning rate, how big the optimizer's steps are, the batch size, how many samples per update, the number of epochs, how many full passes through the data, the choice of optimizer itself, or even architectural choices like the number of layers or hidden units in your model.
And getting the hyperparameters right is important.
It's often critical. Tuning hyperparameters can be the difference between a model that learns beautifully and one that doesn't converge at all. It's a big part of the experimental process.
Okay, parameters learned, hyperparameters set by us. Now, step 5.
Step 5, build a training loop. This is the engine room. This is where the learning actually happens through repetition. The core idea is to loop through your data multiple times.
These loops are called epochs.
Right. One epoch is defined as a single pass through your entire training data set. You typically train for multiple epochs, say 10, 50, or hundreds, letting the model see the data again and again to refine its parameters. You set the number of epochs as a hyperparameter.
So the outer loop is the epochs loop. What happens inside each epoch?
Inside the epoch loop, you typically have an inner loop that iterates through your data loader, pulling out one batch of data at a time. For each batch, you perform a sequence of crucial operations.
Okay, let's break down the steps within the training loop for a single batch.
All right, first, forward pass. You take the batch of input data, features X, and pass it through your model, model X, which executes the forward method you defined. This produces the model's predictions for that batch hybrid. Make sure both the model and the data are on the same device, CPU or GPU.
Model makes a guess, then.
Second, calculate loss. You take the predictions, hybrid, and the true labels for that batch, true, and feed them into the loss function you chose earlier, loss env, if and f feed my set true. This gives you a single scalar value representing the average error for that batch.
Measure the error for the batch. Next.
Third, and this one trips people up, zero the gradients.
Yeah.
You call optimizer.zeroGrad. Why? Because PyTorch accumulates gradients by default. If you didn't zero them out before calculating the gradients for the current batch, you'd be adding the new gradients to the leftover gradients from the previous batch.
Which would mess up the update.
Completely. It would corrupt the signal the optimizer needs. So always zero gradients at the start of the backward pass calculation for each batch.
Okay, zero grads. Fourth step. This sounds important.
Fourth, the magic happens. Backpropagation. You take the calculated loss for the batch and simply call loss.backward. This single command triggers PyTorch's automatic differentiation engine, called torch.autograd.
Autograd, what does it do?
Autograd looks at the loss value and traces backward through the computation graph all the operations that led to that loss. Using the chain rule from calculus, it automatically calculates the gradient, the derivative of the loss function, with respect to every single learnable parameter, nn parameter, in your model that contributed to that loss.
Wow. So it figures out how much each weight and bias needs to change.
It calculates the direction and magnitude of the change needed for each parameter to reduce the loss. These calculated gradients are then stored in the .grad attribute of each parameter tensor.
Okay, gradients calculated via loss.backward. What's the final step in the loop?
Fifth, step the optimizer. Now that the gradients have been computed and stored, you tell the optimizer to actually update the model's parameters. You call optimizer.step.
And what is optimizer.step?
The optimizer looks at the .grad attribute of every parameter it's responsible for managing. It takes that gradient, applies its specific update rule, like SGD or Atom, incorporates the learning rate you set, and performs the actual subtraction, or modified subtraction, to update the parameter's value. Learning rate parameter.grad, roughly speaking. This nudges the parameters slightly in the direction that minimizes the loss.
And then the loop repeats for the next batch.
Exactly. Forward pass, calculate loss, zero gradients, backpropagation loss backward, step optimizer, optimizer.step. Over and over, batch after batch, epoch after epoch. That's the core training loop.
That clarifies the process immensely. What's the final step? Step 6.
Step 6, save and reload. Training deep learning models can take a long time and be computationally expensive. Once you've trained your model and you're happy with its performance, or even periodically during training, you need to save its learned state.
So you don't lose all that work.
Right. You typically save the model's state dictionary, which is essentially Python dictionary containing all the learned parameters, weights and biases, and their values. You get it using model.stateDict. You save this dictionary to a file, example, using torch.save.
And then you can load it back later?
Yep. Later, you can instantiate the same model architecture and then load the saved state dictionary back into it using model.loadStateDict. This restores the model to the exact state it was in when you saved it, allowing you to resume training or use it for making predictions, inference, without starting from random weights again.
Okay, those are the 6 steps. Seems like a solid framework. And you mentioned the learning rate, LR, earlier as maybe the most critical hyperparameter.
It's definitely one of the most important, yeah. It controls the size of the steps the optimizer takes when updating the weights. Too small, and training will be incredibly slow or might get stuck in a poor local minimum.
Just tiny, tiny updates.
Exactly. Too large, and the optimizer might overshoot the optimal point in the loss landscape, causing the loss to bounce around wildly or even diverge increase. Finding that Goldilocks zone for the learning rate is a key part of the tuning process.
Lots of trial and error, I imagine.
Often, yes. Or using learning rate scheduling techniques, but that's a more advanced topic. For now, understand it's a crucial knob you control.
Okay. This is where the theory hits the road, right? Moving from following a nice, clean tutorial script to actually building your own thing. That's when the problems start.
That's when the real learning begins, some might say. You will inevitably run into roadblocks. It's part of the process.
So let's look troubleshooting. You mentioned common pitfalls. Are there specific errors that beginners hit over and over?
Oh, absolutely. There are 3 errors that account for probably 90% of the frustration when you're starting out with PyTorch, especially dealing with tensors, shapes, and where the computations happen. We sometimes call them the 3 horsemen of PyTorch debugging.
The 3 horsemen? Okay. Sounds ominous. Let's demystify them. What's the first one?
Error #1, wrong data type. This one stems from PyTorch's need for numerical consistency. Deep learning math, especially on GPUs, works best when all the numbers involved are of the same type. PyTorch generally defaults to using 32-bit floating point numbers, torch.float32 or just torch.float.
Okay, so everything should be float 32.
Usually, yes, for standard training. The problem arises if you try to perform an operation like addition or matrix multiplication between 2 tensors that have different data types. For example, if one tensor is float 32 and the other is float 64, a double precision float, which NumPy sometimes defaults to, or maybe an intertype like torch.in64.
PyTorch will complain.
It will throw a runtime error saying something like, expected object of scalar type float but got double, or similar. It's telling you the types don't match.
How do you fix it?
Usually it's straightforward. You need to explicitly convert one of the tensors to match the other's type before the operation. You can use methods like .float to convert to float 32, .double for float 64, .long for in64, and so on. Just make sure the tensors going into an operation share the same dtype.
Okay, check your dtypes. Got it. Horseman number 2.
Error. #2. Wrong shape. Shapes. This is arguably the most common and often the most confusing error for beginners. It pops up whenever a tensor operation receives input with dimensions it wasn't expecting.
Like the matrix multiplication rules we talked about.
Exactly. Violating the inner dimensions must match rule is a huge source of shape errors. Matmul that input dimensions must match. But it also happens when you try to pass data to a specific layer, like n.Linear or n.Convoluted, and the tensor doesn't have the number or arrangement of dimensions that layer requires.
Can you give an example?
A classic one is feeding data to a linear layer, n linear in features, out features. This layer typically expects input tensors of shape, batch size, in features. But maybe your data tensor is currently 3D, or maybe it's just a 1D vector because you processed a single item and forgot the batch dimension.
So the layer crashes because it expected a 2D input.
Precisely. You might get an error related to dimension mismatch. The fix often involves consciously manipulating the tensor's shape before feeding it to the layer.
How do you manipulate shapes?
PyTorch gives you several tools. If you need to add a dimension, like adding a batch dimension of size 1 to a vector, you use unsqueeze_dim. If you need to remove a dimension of size 1, use squeeze_dim. If you need to fundamentally rearrange the dimensions while keeping the total number of elements the same, you use .view or reshape. And as we mentioned, D or torch.transpose swaps dimensions, often needed for matrix multiplication alignment.
So lots of shape-changing tools.
Yes. The key takeaway is print your shapes constantly. Use print_tensor.shape before and after operations, especially before feeding data into layers. Understand what shapes each layer expects. Read the documentation and make sure your tensors match.
Print shapes, print shapes, print shapes. Okay. What's the third horseman?
Error #3, wrong device. This one isn't about the math itself, but about where the math is happening. Tensors and models need to reside on the exact same piece of hardware to interact.
Meaning CPU or GPU?
Exactly. You can perform computations on your computer's main processor, the CPU, or, for the massive speedups needed in deep learning, on a dedicated graphics processing unit, GPU, typically using NVIDIA's CUA platform.
Okay.
The error occurs if, for instance, your model, nn.Module, has been moved to the GPU using model.to CUDA, but the batch of data you're trying to feed it during the training loop is still sitting on the CPU, which is often the default when it comes out of the data loader.
If they're on different devices.
Boom. Boom. You'll get a runtime error clearly stating something like, expected all tensors to be on the same device, but found at least two devices, CUDA.0 and CP.
That seems clear enough. How do you prevent that?
You prevent it by writing device-agnostic code right from the start. Don't hardcode C key or CUDA everywhere.
What does that mean, device agnostic?
It means your code should automatically detect if a suitable GPU is available and use it if possible, otherwise gracefully fall back to using the CPU.
How do you write code like that?
It's pretty standard practice. At the beginning of your script, you typically define a device variable using logic like this. Device CUDA if torch.cuda.I is available. I'll see.
Oh, okay, so it checks for a CD data GPU and sets the device string accordingly.
Exactly. Then throughout your code, whenever you create your model or whenever you get a batch of data from your data loader inside the training loop, you explicitly move it to this chosen device.
Using that dot method. Yep. So you do your model.to device when you create the model. And inside the training loop, for your input features X and labels Y, you do X equals BAB device and Y equals Y.to device.
So everything model inputs labels gets pushed to the same place, whether it's the GPU or CPU.
Exactly. This makes your code portable and ensures you're always using the best available hardware without device mismatch errors.
That's a really important practice. And speaking of hardware, GPUs can be expensive. What if someone doesn't have a fancy NVIDIA card?
That's a great point. Access to compute is crucial. Services like Google Colab are fantastic resources. They provide free, with some limits, access to cloud-based environments that often include powerful NVIDIA GPUs.
So you can run PyTorch code on a GPU through your web browser.
Essentially, yes. It's an incredibly accessible way for beginners and students to get started with serious deep learning training without needing to invest thousands in hardware upfront. Definitely check out Colab if you don't have a local GPU.
Good tip. Okay, one more practical thing. Training is one phase, but what about when you're done training? Just want to use the model to make predictions on new data? Is there anything special you need to do?
Yes, absolutely. This is called the inference or evaluation phase. When you're not training, you need to tell PyTorch two things.
Right.
First, you should put your model into evaluation mode by calling model.eval. This turns off certain layers or behaviors that are only used during training, like dropout, which randomly zeroes out neurons to prevent overfitting, and batch normalization, which updates running statistics during training but should use fixed stats during inference. Model.eval ensures consistent prediction results.
So model.eval before predicting. What's the second thing?
Second, you should wrap your inference code within a context manager called torch.inference mode, or the older torch.integrad.
Like that.
What's this?
What does torch.inference mode? It tells PyTorch that you won't be needing gradients for any calculations inside this block, since you're not training or calling loss.backwards. This disables the gradient tracking mechanism, autograd, which saves a significant amount of memory and can speed up your computations.
So model.eval sets the model's behavior, and torch.inference mode turns off gradient tracking for efficiency.
Exactly. Use both when you're testing your model or deploying it for predictions. Remember to switch back to model.train if you resume training later.
Got it. These practical tips, checking types, checking shapes, managing devices, using eval inference mode seem crucial for avoiding headaches.
They really are. They form the bedrock of smooth PyTorch development. And ultimately, the mindset you bring to this matters just as much.
The mindset.
Yeah. We mentioned it earlier. Approach deep learning like a combination of a scientist and a chef.
Scientist and chef. How so?
Be rigorous like a scientist. Document your experiments. Carefully track your hyperparameters, learning rate, batch size, etc. Plot your training and validation loss curves to see if the model is actually learning or overfitting. Be systematic.
Okay, the methodical part. And the chef.
Be creative and curious like a chef. Don't be afraid to try things out. Swap out a layer. Add another one. Change an activation function. Tweak a hyperparameter just to see what happens. Mix and match components. Sometimes the best results come from playful experimentation, guided by the scientific tracking.
I like that. Rigor and experimentation combined.
So far, the models we've implicitly discussed, maybe using just nlinear layers, have a significant limitation.
Okay, what's that?
A model composed only of linear layers, which perform matrix multiplication and add a bias, can only ever learn linear relationships. It doesn't matter how many linear layers you stack, the end result is still just a linear transformation of the input.
So it can only draw straight lines or flat planes to separate data.
Exactly. It can fit a straight line through scattered points in regression, or find a flat hyperplane to separate classes in classification. But the real world is rarely that simple.
Yeah, data patterns are usually curvy, complex.
Precisely. Think about data clustered in, say, two concentric circles on a graph. One cluster in the middle, another forming a ring around it. How do you separate those with a single straight line?
You can't. A line would cut through both circles.
Right. A purely linear model would fail miserably on that task. That's why nonlinearity is key for deep learning to model complex patterns.
How do we introduce nonlinearity?
We insert nonlinear activation functions between the linear layers in our network. These functions take the output of a linear layer and apply a nonlinear mathematical transformation to it before passing it to the next layer.
So linear layer, nonlinear activation, linear layer, nonlinear activation, like that.
That's the basic building block of most feed-forward neural networks. The linear layer does the learnable transformation, weights and bias, and the activation function introduces the complexity, the ability to bend and curve.
What does the math look like? A linear layer is like dollar equals plus b baller. What does the activation do?
The activation function, let's call it $5, is applied element-wise to the output dollars. So the output of the activation is Fy equals Fwx plus b. This breaks the pure linearity. The network is no longer restricted to fitting straight lines. It can learn much more complex curved decision boundaries.
What are some common activation functions PyTorch provides?
There are many, but a few are extremely common. Probably the most popular default choice today is nn.RALU, the rectified linear unit.
ReLU, what does it do?
It's incredibly simple. It takes an input number, and if the number is positive, it leaves it unchanged. If the number is negative, it sets it to 0. So fx at phase is 0x.
That's it, just clips negative values to 0. That's nonlinear.
It sounds simple, but yes, that sharp corner at 0 is enough nonlinearity. It works surprisingly well in practice, it's computationally very cheap, and helps mitigate some problems like vanishing gradients that plagued older functions.
Okay, ReLU is common. Any others?
Another classic is nn sigmoid. This function squashes any input value into the range between 0 and 1. It produces an S-shaped curve.
Sigmoid, 0 to 1. That sounds useful for probabilities.
Exactly. It's often used in the final layer of a model for binary classification, where you want the output to represent the probability of belonging to the positive class. There's also ntan, hyperbolic tangent, which squashes values between -1 and 1, and others like leak-your-LU, GLU, etc. But ReLU is a great starting point.
So adding these nonlinearities between linear layers is crucial for learning complex patterns.
Absolutely essential. Without them, your deep network collapses into a single linear layer, mathematically speaking.
Okay, now that we have nonlinearity, we can start building more specialized, powerful architectures for specific data types, right? Like images.
Exactly. This brings us into the realm of convolutional neural networks, or CNNs. These are the workhorse architectures for most computer vision tasks.
Computer vision understanding images.
Right. CNNs are specifically designed to process data that has a grid-like topology, like an image. Remember, we represent images as tensors, often 3D, color channels, height, width, or 4D if you include the batch dimension.
Okay, what's the core building block of a CNN? It's not just nn.Linear, right?
No, the key component is the convolutional layer, typically nn.Conv2 in PyTorch for 2D images.
Convolutional layer. How does that work differently from a linear layer?
A linear layer connects every input neuron to every output neuron. It looks at the entire input at once via matrix multiplication. A convolutional layer works differently. It uses a small kernel or filter. Think of it as a small sliding window, maybe 3 by 3 or 5 by 5 pixels in size.
A small window slides across the image.
Exactly. This kernel, which contains the learnable weights for the layer, slides across the input image tensor, region by region. At each position, it performs an element-wise multiplication between the kernel's weights and the patch of the image it's currently covering, and then sums up the result to produce a single value in the output feature map.
So it's looking at small, local patches of the image.
Precisely. The idea is that important visual features like edges, corners, textures are usually local. By sliding this kernel, the layer learns to detect these specific local patterns regardless of where they appear in the image. This is called translation invariance, and it's hugely powerful for vision.
So one kernel might learn to detect horizontal edges, another might learn vertical edges, another a specific curve.
Exactly. The layer learns multiple kernels simultaneously, each producing its own feature map, highlighting where its specific pattern was detected in the input. The output of an nconv tutor layer is typically another 3D tensor, or 4D with batch, representing these detected features.
Okay, that makes sense. Convolutional layers detect local patterns. What other common layers are found in CNNs?
Another very common layer often paired with nconv2 is the max pooling layer, nn max pool tapping.
Max pooling. What's its purpose?
Pooling layers are primarily used for downsampling or compressing the feature maps produced by the convolutional layers.
Why compress them?
Two main reasons. First, it reduces the spatial dimensions, height and width, of the tensor. This dramatically decreases the number of parameters and computations needed in subsequent layers, making the network faster and more memory efficient.
Okay, efficiency. What's the second reason?
Second, it provides a form of robustness. Max pooling typically works by taking a small window, say 2 by 2, over the feature map, and outputting only the maximum value within that window, discarding the rest.
Just the strongest activation in that little region?
Right. This means that even if the exact position of a feature, like that edge the convolutional layer detected, shifts slightly within the input image, the max pooling layer is likely still going to pick up the strong activation. It makes the network less sensitive to small translations or distortions of the features.
So nn.Conv2det learns the features. nn max pool 2det makes the representation smaller and more robust.
That's a good summary. A typical CNN architecture often involves stacks of conv pool layers, progressively learning more complex features while reducing spatial dimensions.
Now, when building these models in PyTorch, are we manually writing out all the sliding window math for convolutions?
Oh, heavens no. That would be incredibly tedious and error-prone.
Mm-hmm.
This ties into the modern PyTorch model building philosophy.
Which is?
Leverage the pre-built, highly optimized layers provided in the torch.n module as much as possible. Your job isn't usually to implement the fundamental math of a convolution or a linear layer. It's to compose these existing building blocks into effective architectures.
Like Lego bricks.
Exactly like Lego bricks. You grab an n-linear brick, an nn.Conv2d brick, an nn.Bart-all-u brick, an n-max-pool-sadat brick, and you stack them together.
How do you stack them easily?
The n-sequential container is incredibly useful for this. It allows you to define a sequence of layers simply by passing them as arguments in the order you want data to flow through them.
So something like model and sequential nn.conv2d, nn.nmeaeu, nn.maxpool2d, nn.flatten nn.linear.
Precisely. nn-sequential handles passing the output of one layer as the input to the next automatically. It makes defining straightforward, feed-forward architectures very clean and concise. Your main task then becomes figuring out the right sequence of layers and, crucially, making sure the input and output shapes, like in channels, out channels, in features, out features, match up correctly between adjacent layers.
Let the building blocks do the heavy lifting, focus on the architecture and the shapes.
That's the essence of practical PyTorch model building today. Define the structure, let PyTorch handle the optimized execution. #tag outro.
Wow, okay. We have really covered a lot of ground here, a pretty comprehensive deep dive into the PyTorch world.
We definitely went through the key concepts.
We started with the big picture, establishing PyTorch's place within that AI, ML, DL hierarchy, and really highlighting why it's so popular, especially that dynamic computation graph advantage.
Yeah, the flexibility aspect.
Then we drilled down into the absolute foundation, the tensor, understanding what it is, the different dimensions, scalar, vector, matrix, and those absolutely critical, non-negotiable rules of matrix multiplication. Inner dimensions match, outer dimensions define shape.
Can't emphasize shapes enough.
Absolutely. Then we laid out that universal 6-step workflow. 1, get data ready, data set, data loader. 2, build model, nn.Module, forward. 3, pick loss function. 4, pick optimizer. 5, build training loop, and 6, save or load.
The blueprint for almost any project.
And within that loop, we dissected the key steps. Forward pass, calculate loss, zero gradients, super important, then the magic of backpropagation with loss.backward and autograd, and finally optimizer.step to update the weights.
The core learning cycle.
We equipped everyone with troubleshooting tactics for those 3 big errors. Wrong data type, wrong shape, tensor.shape is your friend, and wrong device, device agnostic code. Plus, the importance of model.eval and torch.inference mode for prediction.
Essential practicalities.
And finally, we scaled up, explaining why nonlinearity, like NRELU, is absolutely essential to move beyond simple lines, and how CNNs use specialized layers like n.convt and nn.Maxpool2 to understand complex spatial data like images, often built easily using n sequential.
From linear to complex patterns.
So after all that, what does this all really mean? When you're sitting there staring at a blank Python script, what's the core takeaway?
I think the core takeaway is this. The entire goal of this whole complex process, all the tensors, layers, loops, optimizers, it's fundamentally about taking a set of initial random numerical encodings, the model's weights, and methodically adjusting them based on feedback from the data, the loss, until those numbers stop being random and start accurately reflecting the underlying structure of the patterns present in your data.
So it's just finding the right numbers.
It's a process of finding the right numbers through calculated iterative adjustment, and PyTorch provides arguably the most flexible, powerful, and researcher-friendly toolkit available today for performing that adjustment efficiently.
Beautifully put. Okay, so for our final challenge to you, the listener, your experiment.
I'm going to be the chef and the scientist.
Exactly. Remember that analogy. The real core of mastering PyTorch or any deep learning framework isn't just memorizing the API or the workflow steps. It's about relentless, measured experimentation.
You have to try things.
So here's your first experiment. Find any simple data set you can get your hands on, maybe something slightly nonlinear, perhaps those two concentric circles we talked about, or something similar. First, try to fit a purely linear model to it, just n linear layers, maybe one or two. Train it, plot the loss curve.
You'll likely see the loss plateau pretty high. It won't be able to learn the nonlinear pattern.
Right. Then make one change. Add a single nonlinear activation function, like NRAO, right after your first linear layer. Keep everything else the same. Retrain the model.
And watch that loss curve.
Observe how...
Go see the difference nonlinearity makes firsthand. That's where the understanding really clicks. Try it, break it, fix it, and learn from it.
Couldn't have said it better myself. Happy machine learning.